Let's talk about coordination complex nomenclature, or in other words, the set of rules we use to name coordination compounds and complex ions. The first step when naming coordination compounds is going to be to obviously identify the metal. And we can have scenarios where we have two different types of charge for the overall species. Number one is going to be cations. So if the species is cationic, then the rule in those cases is that you just name the metal as it is. An example of this is going to be anytime you have a metal that is cationic, meaning a positive charge. So let's say iron 3+. We would call iron 3+ just the normal name, and then place the charge in Roman numerals in parentheses next to the metal. So in this case, I've identified that iron is cationic. It has a 3+ charge. So then you just name it as it is, so iron 3. Alternatively, we may end up with coordination compounds or complex ions that are in fact anionic. An example of this is something like iron hexacyano, hexa meaning the 6, cyano meaning the cyano ligands, that has an overall charge of 4-. Now I know that cyanide or cyano ligand has a 1- charge. There are 6 of them, and those 6 1- charges are balanced out by 2+ iron for an overall balance of charge of 4-. So in this case, overall, the complex is anionic. So for that reason, when we identify the metal in this species, which is just iron, that part of our nomenclature, when we go to name this compound, we will include other things. But for the metal, we will actually change the name. So in this case, this would be hexacyano, because there are 6 cyano ligands. And then instead of writing iron with the charge, we'll actually change the ending to ferrate. So we have changed the ending to ATE or 8. And then you still need to include the charge of the iron species as a Roman numeral. So in this case, it would be hexacyanoferrate 2, because the charge on iron in this case is 2+. The next step in naming coordination complexes is going to be to identify and name the ligands. Importantly, you should always write the names of the ligands in alphabetical order. Additionally, if the ligand has a Greek prefix, you need to include it. So an example of this, a common ligand is a phosphine ligand. And if we have, for example, PPH3, this is called triphenylphosphine. So this is triphenylphosphine. And you need to make sure that you do include the Greek prefix if the ligand itself has that in it. Some other common examples of ligands that we're going to encounter in our class and in others are things like NH3. Now this is ammonia, however, as a ligand, because it's so common, it actually gets its own unique name. It's called an amine ligand. This is an amine with 2 M's. Water is also another very common ligand for coordination compounds. And rather than naming it water, we actually call it aquo. So aquo or aqua, sometimes you will also see it. Aqua or aquo is the name of the ligand when water is the ligand. We already saw an example where you have cyano as a ligand. CO is another common example. This is called the carbonyl ligand. And in class, we'll talk about some of the other common types of ligand structures. The next step is to count the total number of each type of ligand. An example of this is, let's say we had cobalt with 3 amine ligands and 2 chloro ligands. I would say that these need to be assigned their Greek prefix to indicate how many of each type of ligand we have. So for amine, because there are 3, we call that tri. So this is tri amine. For chloro, there are 2, which means that I need to put the Greek prefix di beforehand. So we have mono, di, tri, tetra, penta, hexa, hepta, octo, all those same Greek prefixes that you learned about in general chemistry for nomenclature of, for example, covalent molecules. Those still apply here, and you need to include them when indicating how many of each type of ligand. Now, importantly, and you saw this example on the previous section of this video, we talked about the triphenyl phosphine ligand. And this one already has a Greek prefix in it. A part of the ligand name has a Greek prefix. And we mentioned on the last step that you need to include the Greek prefix if it's in the name of the ligand. So what would we do then if, for example, we had palladium with 4 triphenylphosphine ligands attached to it? We actually need to switch the prefix or add an additional prefix. So we are still going to call this triphenylphosphine. And in this example, we'll also go ahead and include the palladium. So palladium, and in this example, because triphenylphosphine is a neutral ligand, palladium doesn't have any charge, so palladium 0. But I need to indicate that there are 4 of these. And the way that you indicate 4 is with the new prefix tetrakis. So the secondary Greek prefix for this is going to be tetrakis. For 3, it is tris. And I'll show other examples as we talk more about this in class, which means then that this is not just triphenylphosphine palladium 0, it is tetrakis triphenylphosphine palladium 0. The next step is something that I've already talked a little bit about, but it bears repeating because students often struggle with determining the oxidation state of a metal. And in truth, there's a relatively simple trick. Assume that there is a covalent bond formed between the ligand and the metal. If you were to take those electrons involved in that covalent bond and place them back on the ligand, so in an example of this, so let's say you had iron bound to Cl. If you were to take these ligands and place them back on that chloro ligand, then this chloro then has a full octet of electrons. And this is chloride, the anion chloride. So if this was a neutral 1-to-1 ratio that balanced out the charges between the metal and the ligand, then if there was a single chloride ligand attached, then there would be a single 1+ charge. So similarly, for FeCl3, I know that each chloride is a 1- charge, and because there are 3 of them, that is a 3- charge, which means that in this case, iron has to be a 3+, which means that when I name the metal, this is going to be iron 3. Let's do another example. NH3 is ammonia, or in the case of the nomenclature rules for naming coordination complexes, the amine ligand. But ammonia by itself, NH3, if you were to give the electrons back, is a perfectly neutral species, which means that it doesn't contribute anything to the oxidation state of the metal. However, again, we see that we have 2 of these chloride ligands, or chloro as they're called in the nomenclature rules for coordination complexes. Then I know that overall this is going to be cobalt 2. Let's do another example. CO is the carbonyl ligand, and it doesn't have any overall charge. If you were to calculate the formal charges, you would find that part of it is partially positive, part of it is partially negative, but formal charges are just a formalism. They don't actually mean anything. Either way, both of those charges balance out, and overall, CO is a neutral molecule. Therefore, the CO, or the carbonyl ligands, in this compound do not contribute anything to the oxidation state of manganese. The only one that does is that fluoro, which is fluoro, or fluoride, it is a 1- charge. Therefore, manganese in this compound has to be manganese 1. The final step is to include any counterions, if they're present, following the rules of ionic compound nomenclature that you would have learned about in general chemistry. An example of this would have been KCl, for example, potassium chloride. We name it that way because we know potassium can only have a 1+ charge because it's not a transition metal, so it's just the cation followed by the anion. Similarly, coordination complexes, as we've seen today, can form anionic species. The example that we looked at previously was this hexacyano iron 2+ compound, or which we called ferrate because it has an anionic charge. And anytime you have an anionic coordination compound, you change the ending to ate, A-T-E. So, oftentimes what you'll see is the full ionic compound of something like this. So we know that this overall has a 4+ charge, or a 4- charge, but what you may see instead is the full ionic compound. An example of this might be Ca2 followed by the rest of our complex ion. So a complex ion is a coordination compound that forms either a cationic or anionic species. So I know that calcium is an alkali earth metal. It always has a 2+ charge. So calcium is always 2+ in its ionic state. There are 2 of them for an overall charge of 4+. So that is going to create this neutral ionic compound. So how do we name something like this? Well, as we have already seen, the part of the complex ion, we said was hexacyano, meaning 6 cyano ligands, ferrate with a 2+ charge, and overall, remember, 2+ plus 6- is 4-, is balanced out by the 2 calciums with a 4+ charge. So in this example, you just write the name of the cation followed by the name of the anion, which in this case was the complex ion. So therefore, this species would just be called calcium hexacyanoferrate 2. And the reason that we don't need to indicate the charge on calcium is because it is one of the metal ionic species that only have a single type of charge. Calcium in its ionic state is always going to be calcium 2+, just like potassium in its ionic state, being an alkali metal, is always going to be a 1+ charge. Now let's put it together and try some of these examples. I'm going to put some examples on the board, and I truly want you to pause the video and try to work them out. I promise that this will aid your understanding and learning if you try them first before I resume explaining how to solve each of the problems. So for each of these, I'm going to take the same systematic approach to identifying the components of the coordination compounds or the complex ions that I can use to help me solve for what is the overall name of each of these different coordination complexes. So the first thing is to identify the central metal. So I know that CO is cobalt, and I know that this is a cationic species. So what's going to happen is that I'm just going to leave cobalt's name as it is, and I'm going to include the charge. I know that each of these amine ligands are neutral. There are 6 of those neutral amine ligands. I know that the overall charge has to be 3+, and since the amine ligand is neutral, then that means that cobalt has to be in the 3+ charge. So as a Roman numeral, I'm going to have my 3 indicating the 3+ oxidation state of cobalt. And from there, all I need to remember is that NH3 is the amine ligand. And now I can actually solve for this problem and name this compound. So this is going to be, remember that the Greek prefix for 6 is hexa. So therefore, I know that this is hexaamine cobalt 3. Now, importantly, and there actually is no universally accepted way to name hexaamine. Notice that there are 2 A's repeating. So if you were to write hexamine instead of hexaamine, both of those would be correct. So either way, I would accept those for full credit. So hexaamine or hexamine, cobalt 3. The next one, I know that Cu is copper. However, importantly, I know that this is an anionic species. So it's not going to be copper. I need to actually change the ending to 8. And when you do that, you need to use the original Greek or Roman name for this metal. And in this example, that is cuprate. So Cu comes from cuprate. And that has the ending of ATE. I also need to identify the ligands. I know that there are 4 chloro ligands. Chloro has a 1- charge. That means that there's an overall 4- charge. And since my complex ion actually has a 2- charge, that means that copper has to be 2+. So this has to be Cu2+, which leaves behind, after balancing out with the ligands, a 2- charge, which is what I have on my on this complex ion. Which means that now I have enough information to go in and name this. So I know that 4, the Greek prefix, is tetra. So tetra, the ligand is chloro. And then I know that this is cuprate. And I know that the charge of that metal is 2, and I need to indicate that. So the reason that we indicate the charge is because transition metals can take on multiple charges. So it's important to indicate the oxidation state of the metal when naming coordination compounds and complex ions. Now for the last example, we have the complete ionic compound. I know that potassium is at the first column on the periodic table, so it's an alkali metal. Potassium is always in the 1+ oxidation state in an ionic compound. I know that there are 4 of them, so this gives me an overall 4+ charge. Okay, so I need to keep track of my charges because eventually I have to determine for my central transition metal what is the overall charge. I know that I have 6 chloro ligands, which each have a 1- charge. That's a total of 6-. So if I have a 4+ from my potassium and a 6- from my chloro ligands, then that means that in order to make this a perfectly balanced net 0 overall charge, that my central metal has to be in the 2+ state. Now, if I go to the periodic table and I look up Ru, that is ruthenium. So it's ruthenium, and importantly, it has a 2+ oxidation state. Now, remember that this part of the complex ion is negatively charged, which means that I can't just call it ruthenium. So I actually have to change the ending to ruthenate. Remember, the ending for negatively charged complex ions has to be changed to ATE, and I will put in the 2+ as a Roman numeral to indicate the oxidation state. All right, so how do I name this part right here by itself? So that is hexachloro, because I have 6, which is hexachloro ruthenate 2. And then I need to remember that if I have a complex ion, I also need to include the cationic species, which in this case is potassium. And remember, in naming ionic compounds where one of the metals can only take on a single type of charge, like alkali metals and alkaline earth metals, then this means that I just leave it by itself and I don't need to put how many in my naming. So I wouldn't put tetra and I wouldn't put the charge. So this is potassium hexachloro ruthenate 2. And this is how we name compounds, and we'll do some more examples in class.